co-organizer and chairman of today's first meeting. So we are now in week 2 of the program. I've introduced much about Nobita and the program activities during last week, and I don't think I need to repeat that every week. But please ask questions, of course. Today, Jonas will be sharing this talk today, and after that we will begin with a brief planning session for the rest of the activities, both during this week and also partially the following weeks after that. So that will be a joint discussion after that, and then we have lunch at 12:30 roughly down at the canteen, which is in the level 3 of the main building, of the Adenauer building. Lunch costs 65 krona. If there's a choice of 3 different meals, meat, fish, and vegetarian. You would normally need to ask for the vegetarian dish. It's not normally put up on display. If it's up on display, you can just take it. That's normally fresh and warm. It's not only for display. It is freshly made. You just take it from there and then there's a full new one. So I think these are the important things about lunch. So 65 krona if you have just water. If you have some other juice, it's slightly more. And if you take bread, for example, it's also more, and stuff like this. You'll get an idea from this from the local people, I believe. And that's it then. So Jonas, please.
Yes, thank you. I could perhaps add that I'm an oceanographer, and I work at the University of Stockholm in the meteorology department, which is the next subway stop, 1 kilometer. So I will be here, not during the whole program, but occasionally I will be at my own department, but on and off I will be present here. And so today, let me introduce today's speaker, Professor majumdar, and who is a professor at the Rosenstiel School of Marine and Atmospheric Science in the University of Miami. And from my perspective as an oceanographer, I can say that this is at least one of the 10 or perhaps fewer than that, the leading centers in the world for oceanographic audio. It's also a good place for atmospheric science. Farhan, he took his bachelor and also PhD from Cambridge, at the DAN, Department of Applied Mathematics and Theoretical Physics. I was also there myself. So he took his PhD in 1997 in meteorology, and he's been working mainly in meteorology since then. And he was then a postdoc in Penn State, and from there he went to Miami in 2000, first as a postdoc, and then now as professor of quantum faculty. And his field is meteorology, as I said, and in particular then data assimilation, predictability, and also hurricanes. And today he will make a more general talk, suitable also for the students. That's why we put it today. About adaptive sampling. And on Wednesday we will talk about hurricane forecasting.
Great. Well, thank you very much for a kind introduction, Jonas, and thanks to you and Axel and others for inviting me to the Northeast program. It's been great fun for the last week, and I have a lot of objectives here, and I feel they're being fulfilled. Some of it being to help develop a new course in Miami. The meteorology program is still relatively young. It's only a decade old. I got there just sort of to try and help build it and have sort of a bit of an emphasis on tropical meteorology. But what I'll be talking about today will actually be more sort of from what I did for my postdoc, which was when I actually started meteorology, that my PhD was in applied mathematics and acoustics. But then I went to Penn State and I worked with Craig Bishop, who Pavel referred to many times last week. And what we did was we developed the ETKF for use in adaptive sampling. So the purpose of this is really sort of to extend some of what Pavel and Olivier presented and educated us on last week. And just in the context of adaptive sampling, which we'll introduce in just a few minutes. Oh yeah, before we go to the next slide, yeah, that's my website, so there's all my papers and a lot of details, my research and everything along there. And this is where I work and live. This is Key Biscayne. It's a little island off Miami, population 10,000. I live in this building here. There's a big tennis tournament that just concluded here, and I worked at that, and all the famous tennis players come to that. Oh, sorry. Thanks. Yeah, just kind of hard to see here, but it's within here. Yeah, Novak Djokovic won the men's final. That was great fun, real pleasure to be at that game. He beat Nadal in 3 sets. And the commute is down to Virginia Key, which is actually an unpopulated island except for some birds. Here is our campus. So this is not the full campus of the University of Miami, but just the Rosenstiel School for Marine and Atmospheric Science. So my building's here, and then there's departments of the geophysics, geology, oceanography, marine affairs, marine biology, and that little meteorology group, which is all on the top floor here. And then we're across the street from the National Oceanographic and Atmospheric Administration, or NOAA, and they have a Physical Oceanography Division and Hurricane Research Division here, and they do quite a bit on data assimilation as well. So we have close collaborations, being physically not that far away. And then Lolita, the killer whale, lives in here. So if any of you are ever passing through Miami, then drop me a line. I'd be more than glad to show you around. So what kind of science do I do? Well, this is what I was doing during my postdoc and then the first few years in Miami. I still do a little bit, but I've really, as Jonas mentioned, moved really into hurricanes. But really, what I started off in meteorology is just figuring out what this adaptive sampling is and how to optimize a future estimate of the state given some available mobile observational resources, and we'll talk about that in the next slide. And so the very basic timeline here is that we need to make a decision at some point, like say today, on where to sample, say, extra aircraft observations or activation of a particular satellite scanning mode in order to improve a state estimate of something, be it a weather forecast or be it some sort of forecast of a process in the ocean, although we haven't really done much of the ocean stuff yet. But this is the main timeline that we'll be thinking about all the way through here. So there's a fairly complicated diagram that was produced by Alexis Dorenbecher. Well, I'll have to use the space bar, the remote thing's not really working. From Météo France. And so it takes a little while to process what this diagram means. So he set up this timeline right here. And essentially this is our initial time. And we want to optimize our resources by adaptively sampling them at this time, although it could in principle be a series of times, in order to improve some state estimate of a forecast at a future verification time or forecast time, and within some verification region. So a question here is, well, here is the 500 millibar geopotential height. And this essentially, for us non-meteorologists, is saying that there could be a weather system somewhere here in southern Europe. And so the question is, well, if we see this a few days in advance, and if we have some mobile adaptive observational resources, then how should we deploy them at some earlier time to improve this future forecast of this potentially serious weather system? So the idea is to, well, choose the forecast at hand, which could be this, and then produce a sensitive area calculation, which is essentially this. And so much of the topic of this talk is just how we proceed to provide these sensitive areas. And once the sensitive area calculation has been provided, then a decision can be made on when or whether to deploy adaptive observational resources, and then to make a request. And so types of platforms that can be deployed are typically research aircraft. They can release these drop windsons here. These basically are like weather balloons, but they're on a parachute. That they measure temperature, humidity, pressure, and then also winds just from its drifting and that being caught on GPS. Research vessels which may launch weather balloons or just have their own in situ observations, and the balloons that are launched also from land. And so these platforms can deploy various systems. And something I'm not going to talk about today, but I'm getting into, is targeted satellite sampling. So over the last decade, there have been several field programs that have involved all of these adaptive sampling type capabilities. And what I was focused on more in the early part of the last decade was devising a technique to compute these sensitive areas. Yeah, sorry. Yeah, please ask questions.
I'm not sure, I don't see it so well, but is it over land or over sea, the area you wish to look at? Because if it's over land, you will have a lot of remote, already some sensors locally on the ground. So I guess it's more when you are in a kind of isolated or desert-like space that you want to do this sampling.
Yeah, you're exactly right. That especially over Europe and over North America, that the routine network for weather balloons is fairly dense, at least on the scales at which much of these weather phenomena are being predicted, which are sort of order 100 to 1,000 kilometers. So, it's supposed that that's a fairly adequate observational network. And so it's really over the ocean that satellite observations are typically not, they don't have the right vertical structure, particularly in areas where the wind and temperature fields change a lot with height. So those areas could be a baroclinic zone, for example. And there it's suggested that we may need more observations, so typically more over the oceans where we don't have these in situ data. And having said that, satellite data are getting better, but there's still a lot of challenges in cloudy regions. And so philosophically, what would we want out of these adaptive sampling strategies? They need to account for a lot of things. We should account for the type of event and the type of metric. What forecast metrics we want to improve, be it precipitation, be it winds, should they be at the lower levels or the upper levels? And there's still a lot of debate and controversy about even this very basic thing. Then we need to think about the regular observations, such as the weather balloons that are launched every 12 hours, that have been and will be used. Then, of course, central to all of this, and the reason I'm giving this talk, is the data assimilation that's used to assimilate the routine and the adaptive data. What types of adaptive observations are to be sampled, so their variables and their error characteristics. And then also, and this is where it's a little different from the data assimilation that we learned last week, is that we'd like to try and project the influence of assimilating these observations on the forecast. So before we get into some of the theory, I'd just like to outline some of the talks that I'll be giving. So the rest of this talk is going to be mainly a theoretical background of the ETKF, and then, if time permits, also some singular vectors. Then on Wednesday, I'll give a talk on hurricanes. I have 12 projects on hurricanes, and that's what I'm massively into right now, and that's what all my students are doing. Then I'll be heading over to Bergen to visit Pavel and talking a little bit about theory and applications, but a little bit of a mix of this talk and the other talks. And then at the university next week, I'll be giving a talk on winter weather, which will be a little bit more applied than this talk here. It will sort of be like a follow-on from this talk where I won't go so heavily into the theory, but I'll talk about some of the characteristics of targeting and whether the field programs have been successful and things like that. So it'll be a much more applied talk at the university, and you're all more than welcome to come to that. So now let's dive right into the ETKF. So I'll be building mainly on what Pavel introduced last week. So we developed this a decade ago, and it's been used for every year in the last decade in winter storm reconnaissance missions. And so the idea here, and this is just in the US, is that if a winter weather event is anticipated to produce some rain or snow in the US, then there are aircraft that can be flown out of Alaska, Hawaii, or based on some of the more recent work, Japan, to release these drop zones which plunge from the aircraft at about, oh golly, I'm going to say 45,000 feet. How many meters is that? That's about 15,000 meters down towards the ocean surface. And so it takes very detailed measurements as they go down. These aircraft release typically about 20 of those per flight. And so the ETKF produces the sensitive area calculations that are still used in these annual programs. And there have been many other field campaigns in which the ETKF is used. And I'll show just a few examples of those near the end of this talk. But I'll show more on the hurricane stuff on Wednesday, and then more on these World Meteorological Organization supported campaigns, many of which were run in Europe. I'll present next week at the university. And then I've dabbled a little in coastal ocean sampling, but the models have been horrible and we've struggled to really get meaningful results. So what is the ETKF? Well, it's one of the family of ensemble square root filters, and Pavel mentioned most of these. The one that wasn't discussed was this, which was derived at Harvard, particularly with oceanographic applications, and with a very forbidding notation that no one could really understand what it was. But this was actually developed at the same time as the ETKF, and they're theoretically equivalent techniques. And so these are all part of a family of square root filters, where essentially an ensemble of forecast perturbations is converted into an ensemble of analysis perturbations via some transformation matrix. And so Pavel drew these up last week, and essentially, just because we've had a weekend and we've rebooted our brains, I'll draw it again. That these matrices of ensemble perturbations, that they essentially have these columns that represent all the state variables, and the perturbations are computed about an ensemble mean. And then here are just 4 realizations here. So this is like with a 4-member ensemble here. I mean, typically it's about 100 ensemble members that are used in data simulation for our adaptive sampling. So when we talk about a matrix of ensemble perturbations with that notation, then we're talking about this, which Pavel introduced last week. And then our transformation matrix is this matrix here, which is k by k, where k is the number of ensemble perturbations. And so this is a fairly simple linear transformation to do. And one thing that's necessary here with adaptive sampling is that it needs to be fast, because it's done in real time. And as we'll talk about, we look at potential different observational networks here. So the main principle is that in all the square root filters, that the prior or forecast error covariance matrix is written as an outer product of these matrices that comprise the ensemble perturbations. So we learnt all of that last week, and don't feel we really need to justify it. And this is just this. And then the analysis perturbation is essentially represented by this transformation matrix. And this matrix is computed based on the network of observations that we have. So this is just the how it's used in data simulations. There's nothing that's earth-shatteringly new here. So here's a covariance update. Now, what we're talking about here is that we're talking about future sets of adaptive observations. And so we don't actually know what the value of that observation will be. So we actually are doing all of this in error statistics space. So we're not doing just the Kalman filter update of a specific state estimate. That we're just going to talk about it in terms of the error statistics. And so this is essentially just the Kalman filter error statistics equations that show how the forecast error covariance, or the prior error covariance, is reduced due to the assimilation of observations with error characteristics R and the observation operator H. And I should also emphasize that for what we're doing, it's all in linear world here. So this is our main matrix here, and we're trying to essentially compute how future sets of observations may reduce the error variance, and therefore suggest which observations are most likely to improve our forecast the most. And so the next couple of slides are going to show a fair bit of matrix algebra just to determine, well, how do we optimize the efficiency of the update of this? So these are pretty big matrices, and it's a little bit nasty to invert. So we developed the ETKF in order to reduce our computations to the subspace of the lowest dimension wherever possible. Whereas a method such as the EAKF that Anderson developed, that the transformation matrix there would be order of 10 to the 7th square and be pretty tricky to update for multiple potential deployments. So we needed to be computationally efficient here. And so there are a few algebraic steps here. First is a very simple one, that we really focus on this stuff here and inverting this this sum of the background error covariance matrix and the observation error covariance matrix interpolated in the observation space. So all we do here is essentially write H star equals H r to the minus a half. So all we've done is just taken factors of r to the minus a half, just to essentially get this to be the identity here. So there's nothing very exciting that's done here, but it just gives us this equation down here. So that's fairly straightforward, nothing too exciting. So this just carries over from the last slide. And then the next stage is that we'd like to factorize this. And so P is just Z transpose. And it possesses K, which is order 100 degrees of freedom. So let's try and get this into that number of degrees of freedom. So it's not explicitly using these big matrices. So there's just a little bit of sort of matrix algebra here, just sort of some identities. And the idea, and this is something that goes a little bit, it's a little different from what Pavel presented last week, is that we actually consider eigenvalue and eigenvector calculations. And so you'll see a lot of C's and gammas showing up in the next few equations in the next couple of slides. Now the idea is that we actually want to break this into an eigenvector decomposition. So one can write any symmetric matrix and do a singular value decomposition as this matrix here. So we have well, this matrix product where we have diagonal matrix of eigenvalues, and then these are this matrix lists orthogonal or rather orthonormal eigenvectors, or rather E transpose E is the identity. So one can factorize the A matrix like this, and there's some degree of arbitrariness as to what C is, although that does get fixed later on. So then A transpose A, which is actually of much lower rank than AA transpose, so it's the same rank, it's of much lower dimension than AA transpose, that just comes out to this. And so then it actually is a fairly easy eigenvalue problem to just solve this, because A transpose A is essentially this transpose times this, so it's a k by k eigenvalue problem to solve. And the whole purpose of this is just to get down to a k by k eigenvalue problem rather than an n by n, or rather an m by m eigenvalue problem where m is the number of observations. So if we just substitute this for A, then what this allows us to do is compute a matrix of orthonormal eigenvectors and a diagonal matrix of eigenvalues. And from there, we can then factorize this rather nasty looking matrix. And furthermore, we'll be able to factorize and do the inversion very easily. So the eigenvalue decomposition of this, which is just A transpose A, is this. And so we can therefore write this messy stuff here as E gamma E transpose, where E is just written as this. So that's all just coming from manipulating those terms. So this is all exact. So if we do that, then here's the nice thing. So we can then write this as E gamma E transpose in here. So that's just a change between here and here. And then furthermore, even if E is not a full rank, and there's a proof in Bishop et al. 2001 for this, I'm not going to go into it here, one can then factorize out the E's. And so we then have E gamma plus I to the minus 1 E transpose. So gamma just houses the k eigenvalues here. So this is just inverting a diagonal matrix now. So that's where the elegance comes in terms of the inversion, and why we went through all this seemingly painful stuff, that we got to this nice thing to invert. Well, the rest of it still looks messy, but even this becomes less messy. We rewrite Z H transpose, or sorry, Z transpose H transpose, so as we're defined here, in terms of the eigenvalues and eigenvectors. And E transpose E is just the identity here. Same on the right-hand side too, it's a symmetric matrix. So then this collapses into something quite simple here. And on this term, which we're just left alone, that one can just add in a CC transpose, since that's just the identity matrix. And so what we come down to here is essentially our analysis error covariance matrix can just be written as an outer product of this matrix here, where we have ZC and then gamma plus I to the minus a half times its transpose. So it drops down into something where these are all just eigenvalues and eigenvectors that can be computed very easily just out of computing this. So that's actually quite fast to do. So I think Pavel computes it a different way, but computationally efficiency really needed to do it this way. And so this is our T in the ETKF. So it's just C gamma plus I to minus half. And then there's any orthonormal matrix, but for our purposes here it doesn't matter what that is, because we're only going to be looking at the variances. So this is the ETKF transformation. So that's the heaviest slide that we have. You'll be glad to know. I love matrix algebra there. So if we get back to the practical problem of adaptive sampling. So it uses the same principle, and we're mapping error covariances forward in time. And although we have to say that this only really holds when linear dynamics hold. And so we want to then account for future routine observation networks prior to deciding where the adaptive observations should be deployed. So the next few slides are just going to build on the theory that we produced and just show how we extend it to future routine and adaptive observational networks. And so we'll do these same kind of transformations appropriate for the different observational networks. So what this does is it takes advantage of serial data assimilation. And Pavel emphasized that quite a bit last week, that the assimilation of each observation one by one is mathematically equivalent to assimilating all those observations at once. And so we exploit that by saying that assimilating any group, breaking any observational network into a set of routine and adaptive observations is the same as assimilating all those observations there together. So we're really just building on some of the applications of what Pavel had introduced theoretically last week. So step one is that we produce an analysis error covariance matrix for the routine observational network, just as we just using this formula. And then the new stuff comes in here. So this is, so the superscript R corresponds to a routine observational network. So ideally we should account for all of our weather balloons and all of our satellite data and everything. In reality we have a much cruder representation of it than that. But if we assume that this is in some way correct, then what we do is we loop over different configurations of a potential adaptive observation network, and then we do the update on our routine analysis error covariance matrix. So essentially, we do this first transformation just once, and then we'll say, okay, at a future time that we want to target the observations, we have this estimate of the routine analysis error covariance matrix. Let's then loop through all our types of adaptive observations. And so this could be, we could run this 1,000 times, and so we then compute these C's and the gammas for each of the 1,000 potential deployments to adaptive observations. And then we get a different reduction in forecast error covariance due to each of the Q's. So Q can go from 1 to 1,000. I mean, Q could go from 1 to 1,000,000. It's just that we needed the efficiency here, hence the previous couple of slides, so that we could produce this in an efficient manner. And so one fairly subtle thing here as well is that I've just kept it for any time t here. Now t could be a future verification time, and then what we're doing is we're just assuming that the transformations to our ensemble perturbations, that it's the same transformation matrix, that it's kept the same, it doesn't evolve between the time that we're sampling and the verification time. So it's essentially saying that we're configuring our ensemble at the time that we're targeting our observations, that we're transforming our ensemble such that it's appropriate for that specific routine adaptive observational network. And then what we do is we just say, well, that same linear combination of ensemble members is what holds for the future verification time, or any future time. So that's a fairly crude assumption there. It makes it computationally very feasible, and I guess just in terms of the principle of it, it's just saying, well, in linear dynamics, that the ensemble perturbations are going to evolve strictly according to just the evolution of that specific transformation of the perturbations. Having said that, we are then taking these perturbations at a future time just by, in the usual ways we do for data assimilation, just subtracting out an ensemble mean from an ensemble forecast that have been integrated out to a future verification time. So this could be like, say, a 3-day forecast from now.
So is
Yeah.
so it's very clear you have hold for any time t if the linear dynamics are obeyed.
Yeah.
But given the observed observational analysis errors, what's a reasonable time to expect the linear dynamics to be obeyed? Is
Yeah.
3 days a reasonable time? Or
Well,
1 day? Or
yeah, it's
8 hours?
interesting that there's a more fundamental question that you ask as well, and that is just when's a tangent linear model acceptable, and over what scales and what regimes? And so, from what I've read, and you can correct me if I'm wrong, I think the paper that sort of explained it best to me was Reynolds and Roseman, 2003, where they suggest that a tangent linear assumption on the synoptic scales, the scales order 1,000 kilometers or so, can hold for about 3 days, at least on those scales. If we're looking at convective scales, then linear dynamics get violated almost immediately. So it all depends on our weather systems of interest. For the targeting that we've been doing, it's mainly been on the synoptic scales, and so it seems like 3 days is okay. I'm not going to show it here, but I will do at Stockholm University next week. And we found that the ETKF actually works when we quantitatively evaluated it. That in some cases it actually works out to even 6 or 7 days.
so what do you mean by works?
Well, essentially it can predict the reduction in forecast error variance. That will become a little bit clearer from the next few slides. And I remember when I gave this talk 5 years ago with these slides, that you had me there for about an hour and a half just saying, just questioning my evaluation method. They were very valid questions, but it was what it was. Evaluating variance is always a tricky thing, but within the parameters of the way we evaluated reduction in forecast error variance, which is still questionable to statisticians, that we found the ETKF was able to at least capture where there'd be a large impact on the forecast from observations, even for 6 or 7 day forecasts. I can show you some of that stuff offline, or I can pull something up if there's time later on. So this is just writing this. So it's just the reduction in the error covariance due to adaptive observations. So PQ is just this thing here. Sorry, PR minus PQ is this thing here, SQ. And we'll just look at this term in a bit more detail the next couple of slides. So it's essentially just this. And the S stands for signal here. So this is where we're now going a little bit beyond what Pavel had presented last week, that we're really looking more at the targeting here. So what I mean by signal is essentially a difference between two state estimates. One state estimate is that with only the routine observations assimilated, and the other state estimate is with the adaptive observations assimilated as well. So here we have an example where a C-130 aircraft flew out of Hawaii, and it released dropsons along this track here. And at NCEP they produced 2 different analyses, one with the routine observations only, with these dropson data withheld, and then the other analysis included the drop-sum data. So NSTEP uses a 3D VAR scheme, and what it did was it produced a signal that was generally quite localized around those observation sites. And the variables that are used here, it's just a kinetic energy signal that's averaged over or through the troposphere. So that's what I mean by signal here. It's just essentially the impact of assimilating a set of targeted observations.
So what is the time here when the aircraft flew and when these forecasts?
Yeah, so in this case, this is just at the very time that the aircraft flew. I'll show the evolution of the signal in a couple of slides. But yeah, this is just to introduce it just at the time that the aircraft flew. And I wanted to put this up there because it's really, and I'll show it theoretically, it's really the variance of this that the ETKF is trying to predict. So this was done 2 days prior to this flight, and so ETKF computes that SQ matrix that was the final equation on the previous slide. And sorry, it was done 36 hours prior to the time that this aircraft flew, and so it also produced a somewhat local signal, although not right at the observation sites. And there are always inconsistencies between them, but it's generally at the right location.
Maybe I missed it, but say again what the SQ is.
Yeah. Sorry.
What
Yeah.
that is.
SQ is the final thing.
Okay,
It's
it's
essentially,
beyond.
if you just remember this is enough. It's the reduction in the error covariance due to sampling the adaptive bars.
And how do you distinguish the fact that they're adaptive versus they're just extra? And if you
I
fly
don't-
from Hawaii to someplace in Alaska, every day on the same path, so it certainly makes sense that you would get a reduction if you take more observations.
Yeah.
So what's the bonus of doing the ensemble with the filter?
Right. The idea is to try and discriminate between what set of adaptive observations might be useful versus set of adaptive observations that might be useless, that may not reduce our, well, it's very, very unlikely to reduce our forecast error at all. So let's say for that case that we have, that there's potential flight out of Alaska here, but if the ETKF predicts a very small signal variance, then, well, we assume that the most likely value of the signal is 0, and so we have like a very narrow distribution here. Whoops. A very narrow PDF. Everything's Gaussian in my world, by the way. A very narrow PDF of the signal centered on 0. So this means that there's a very, very high likelihood that there's a tiny signal. And so we want to look for cases where we have a larger signal variance such that we have some sort of reasonable probability that there's a large signal that's produced. And a large signal should, we hope, correspond to a large forecast improvement. So does that answer your question? It's probably partly there.
If you just ask the forecaster to say what air mass will be over our target region in 3 days, and send the plane there. Certainly, if you send it up to Russia, you're not expecting that air mass to.
Right. Yeah.
How do you make that comparison? Do you fly a plane to something, what's the value added of doing the adaptive observation? That's
Right.
The question
Yeah.
of the machinery versus doing. Eliminate looks at it and says
It's a subjective interpretation of it. Yeah, that hasn't been proven one way or the other. Whether the objective is clearly better than the subjective. What we have shown is that the flights in target areas, or the data that collected in target areas, are more effective at improving the forecast compared with the data in non-target areas, on average. But yeah, that's not a strict answer to your question.
So you have data, you send the plane to non-target areas.
Yeah, there have been some flights that have been taken in non-target areas, or also just in cases where it may still be the optimal target area, but the quantitative value of signal variance is very low. But sometimes they still flew the aircraft anyway. It's an operational program, and people like me are not really involved in it anymore. And otherwise I'd say, well look, we've just got very high certainty in this case, so why do we care about flying? And so there, it's like, even if it's the optimal target for that day, it may still be very low expected signal variance there quantitatively compared with other cases. So we do have some data where the aircraft flew in cases where the signal variance was low.
So this is the target area.
For this case, yeah, that it just flew in a target
The
area.
objective was to improve the forecast.
Yeah, the aim is to improve the forecast downstream. Yeah, I'll get into that in a couple of slides' time. But yeah, we're building up towards, I think, what your question is going to be. But yeah, right now, I just introduced this figure because there's still a theoretical step that we haven't quite completed. And that is just what this variance of these signals actually means. That all we've done so far is shown that we have a reduction in forecast error covariance, but we haven't really said, we haven't shown theoretically what that actually means. So let's look at what a signal is just written in data assimilation world. So it's essentially just a difference between the state estimate of the routine observational network and the state estimate of the routine and adaptive observations assimilated. So it's essentially just this, whereas a Kalman gain operating on the innovation vector, there's a Kalman gain that invokes the adaptive and the routine observations. Then how we compute the covariance of the signals? Well, as the expected value of the outer product of these signals. I should also emphasize that signal is a field here, that this should be in bold font, that these are vectors. And so, essentially, if we just take the outer product of this, then we have the expectation of the outer product of these innovation vectors. So that's what we've got right here. And then just taking the expectation operator inside, we know YQ transpose, that the expected value of that is just the observation error covariance. And then we've got these cross terms, and essentially they boil down to an expectation of the, or correlation between the analysis and the routine analysis and the adaptive observations. And we're assuming that those are uncorrelated here. And then this is also another cross term just with the correlation as well. And then this is just the forecast error, or sorry, the routine analysis error covariance matrix mapped to the adaptive observation side. So essentially, if we strike these out as 0, assuming that they're uncorrelated, and then we end up with this. And if we then just rewrite from our Kalman gain, so there should have been a superscript Q on this, then we come up with this. And this is actually the same as what we had a couple of slides ago. So this is a signal covariance. And this is the reduction in forecast error covariance. And they're actually the same thing.
Well, just a question.
Yeah.
PR contains the terms with different physical nature.
Yeah.
Just about
Yeah. So it's a way just with, yeah.
Just,
Yeah, thanks. Yeah, what we typically are using is just tropospheric wind and temperature, and just for storage purposes, just at 3 levels. Just at 8.
It's sometimes quantitative which are different physical.
Yeah, these are all just physical variables, and essentially they're just taken from the ensemble forecast, from the Z matrices here.
And what's, just while you have it up, what's 1,000 kilometers or 1,000 miles on that previous graph?
Here? 1,000 kilometers.
You're saying that the linear assumption holds on
Yeah.
scales of a
Yeah, the synoptic scales, yeah. So it's typically here Well, about sort of 15 degrees or so, I guess, in the mid-latitudes. Well, it's 0.7 times 111. Yeah, it's probably about 13 degrees or so.
So we should think about points as only being defined within sort of that scale.
Yeah. So what we're doing is we're just trying to sample these features that are of a kind of synoptic scale. So yeah, we're essentially just predicting the covariance of these signals, which I kind of jumped to when he asked your previous question. So it's strictly just suggesting, you know, what's our likelihood of getting a large signal versus getting a small signal. And so we just look at the trace of the signal covariance matrix in the local regions that we're bothered about where the event might occur. So signal variance is really our key quantity here, and it's just computed from some of the diagonal terms of this. Although, as we showed with whole factorization, that those diagonal terms can be computed without the explicitly using the PR matrix. So this is now coming to Jonas's questions. So here's an example of the evolution of the signal over 84 hours here for another flight over Hawaii. So this is just using tropospheric wind and temperature again. So what this shows, it's 12-hour time steps, is just how these two forecasts are diverging. So here we have two analyses that are nearly, or initial conditions that are nearly identical, except for that this flight had taken place in one of them, and those obs were simulated in one and withheld from the other. So we see that this evolving signal, or difference between a forecast, it evolves downstream. It's a positive definite quantity here. And it has a fairly big impact in the verification region that we actually cared about. So this was a nice case in terms of producing a signal that evolved downstream. And it was somewhat clean. The problem is that these signals get very messy. And I published another paper on that with Dan Hodis 3 years ago, just about how these signals are contaminated in operational models. But that opens up a whole can of worms. Now, this is a fun part, is going back and forth between these two slides. So this is the predicted ETKF signal variance that was done 36 hours prior to this flight taking place. The previous slide there, the NSEP signal, that was done after these observations were taken. So this is what actually happened in the operational model after those observations had been assimilated. This is our prediction, at least in a Gaussian statistical sense, of what our variance of those signals is. And being an ensemble filter, it's got some structure to it, even some remote structure here, which may or may not be spurious. But we do see that there's some downstream evolution of the maximum along the mid-latitude storm track. And it does tend to gel somewhat with the actual signal there. And so we did a bunch of these evaluations for different cases. When I did these studies around 2002, that we did them just for short range forecasts, then my student extended it to a 6-day forecast. But I won't show those here. This is just more to explain the concepts rather than the evaluation. However, there is a caveat here that, okay, we had this nice big signal realization here, and it produces a lot of sort of yellow and green colors around the area where we wanted to improve the forecast over the Pacific Northwest. Now this gives the improvement, what is the improvement due to the targeted observations. And the improvement is evaluated against just the NSEP analysis, which of course is imperfect itself, but it's the best that we have. Now, anything that's purple means that the forecast got worse. Everything that's red and yellow and green means that the forecast got better. So actually, even though there was a good signal here that it actually contributed to a degradation of forecast. So this is probably some kind of phase shift here in the weather system of interest. So this is definitely a phase shift right here. So that's just a little caveat that a big signal doesn't necessarily translate to a reduction in the forecast error. That there are other issues there, such as model error, that might come into play.
If you look at the same thing versus the forecast without the adaptive observations?
Yeah, sorry, that's what this is. Sorry, I didn't explain it. This is a reduction in the forecast error due to the adaptive observations. So it's essentially the forecast error with adaptive observations. Sorry, it's the forecast error without the adaptive observations minus the forecast error with the adaptive observations.
So the average looks around 0, which means there's any improvement.
Yeah, it's not really much of a net improvement in this case, yeah.
And in terms of probabilistic, do you run an ensemble?
For this,
I mean,
this is just
sort of bad skills
this is actually just using the operational model, and so there's just there's two model analyses and forecasts that are on here. So this is nothing to do with the ETKF. All the ETKF did was predict where the aircraft, where the best aircraft track would be. This is then just an evaluation. Essentially, first up, computing a forecast error with the operational run that included the adaptive observations, and then computing the forecast error for the operational run that withheld the adaptive observations. So this is just giving a difference between those two. So there's no ensemble in this or anything like that. It's just difference between two
I'm just
forecast
suggesting that
errors.
if you would run the operational ensemble with and the operational ensemble without, and that could actually show that you're getting uncertainty where things are actually uncertain.
Well, you're exactly right. Yeah, you're exactly right, and that would be more strictly compatible with what we try to predict. We try and predict a reduction in forecast error variance due to transforming an ensemble. And so what would be really nice to do would be to have the capability to run an ensemble that's initialized with the adaptive observations in there, and run another ensemble that's initialized without the adaptive observations. And I think that's what you're expecting here, and that's theoretically a more correct thing to do. It's just that we didn't have the capability of rerunning the ensemble.
Okay, well, just again, it's okay. It says if error forecast error for free level UVT.
Yeah.
So so you must have a norm to be able to convert it.
Yeah, it's just a quadratic.
It's
just a total energy norm. It's a half U squared plus V squared plus CP over TR.
And this visit to space shift, you're applying perhaps that it wouldn't really matter too much if something happened 5 hours later, right? Which is probably fair. Can you then take that into account into a revised success map? Which takes that possibility into account?
So it takes, yeah, I mean, that's a really tough one, yeah. My postdoc and I struggle with that, but yeah, that's something where we should probably learn from you and others, is just how to account for phase shifts, because they can look like horrendous errors, and in a very basic way in weather world that we try and verify an improvement of weather forecast. A lot of the time a phase shift kills the statistics. A way to do it could be just in the frame of reference of the weather system itself. So that may be a way to do it, but it needs sort of some way to objectively localize where that system is. And that's something that I'm fairly weak on. I haven't really figured out how to localize on that system, especially if the system's also stretching and shearing at the same time. But I'd be very interested to hear your thoughts on it.
What we noticed in the ocean is that by simulating we add small scales, actually we cannot easily simulate with the model, so we don't resolve them, but we don't simulate it, but we can resolve them, so the observations give, and they give more variability. Actually, instead of reducing the uncertainty, they can add a new uncertainty due to the introduction of small scales.
Yeah, that's certainly a problem that we have here, and it may even have been a player in, or possibly this, certainly probably around here. So yeah, that was a paper, Hodis and Majumdar from 2007 in Quarterly Journal. We looked at exactly that, and we found that even if you made just tiny little perturbations in this same model that are on a scale that's smaller than your synoptic scale, what it can do is that those perturbations can grow into the synoptic scale and contaminate any kind of synoptic scale signal. And I mean, that was a little bit of a disturbing result, but it's something that we need to be careful for. So it's very interesting that you found that for the ocean models. I'd be very interested to see that, and that's a really important point. Because I think that that actually clutters our evaluation of this. And these programs have been going on for a decade now, and we're supposed to summarize, and I'm writing a review article with 19 co-authors on this. And I'm supposed to give some sort of definitive statement about whether these field programs are successful or not. And it's very difficult for me to say one way or the other. And much of that is because these signals, the way that we're evaluating the impact of assimilating targeted observations, it tends to get cluttered so much by the small scales that our signal tends to get a little bit washed down, a little bit weakened as time goes forward.
I mean, one thing would be to actually look at the variance from the ensemble one, which you do have. And
Yeah.
if the variance is high, where the error gets worse,
Yeah.
you shouldn't really penalize yourself so much for that.
Yeah.
But the right thing to do is to do the comparison after a decade of operational runs,
Yeah.
still not have been able to make the ensemble one, which ECMWF hasn't either.
Yeah.
And just compare the probabilities. That's the
Yeah.
way to answer the question.
Yeah.
That's argued when the experiments were set up.
Yeah.
But
Yeah.
they still haven't done the runs.
Yeah, I know. Yeah, that's something that, we've been sort of trying to push. I mean, with ECMWF, they're less interested in this because it's very US-centric. And they did find that there was very little influence in Europe from these Pacific observations.
But from the Atlantic, parallel Atlantic.
Oh yeah. Well,
It's
there's
also
been a
the
few
case
of
they
those
never ran
campaigns.
the
Yeah.
ensemble without the observations again.
That's right. Yeah, they didn't. That's just a big computational burden. It's something that I guess, just even doing the two deterministic runs, that most of the Atlantic trials found, at least in recent years, found there wasn't very much impact on the ECMWF model. Partly because the ECMWF makes such heavy use of their satellite radiances that the impact of drops on data is, or any sort of soundings, non-satellite soundings, especially if there are only like 20 of them, the impact is fairly weak. And so they draw their conclusions really based on that. And so there isn't really much incentive for them to sort of move forward and run off the ensembles. So I think I'll wrap up. I won't get into adjoints here, but I want to just show how the guidance is actually constructed. All I've done so far is build up the pieces of what signal variance is. So how do we construct these maps that actually determine where the aircraft fly? Well, we use existing ensemble forecasts, so NCEP, ECMWF, others now as well. And so these are initialized at least a day before the adaptive observations are taken. And that's just through logistics, that we need to give at least a day of notice to air traffic control and to pilots about where the aircraft should be deployed. And so what we do is we summarize the signal variance predictions as a function of the adaptive observation location. So I'll just wrap up by showing this. So we'll have a look at a case where it's a trivial case, but it's illustrative, where we aim to improve a 24-hour forecast over the western US. And so we can start up here at this at the time at which we wish to make the observations. And we could consider like two sort of pretend sets of targeted observations. One way upstream here, and the other further downstream along a frontal zone. And so this is 24 hours prior to the forecast which we want to verify, which is essentially a frontal system that's just moving towards the western US.
So were these two alternative targets?
These are, both are just ETKF predictions of the signal variance at the targeting time if we're going to place our observations in different locations. What we're building up to here is that, well, we're just going to apply a brute force method by saying, let's just target here, let's target here, let's target here, let's target here. Let's do this 1,000 times for different locations, and then come up with some sort of mosaic or some sort of summary map that tells us, okay, here's a general area where we should really send the planes. So this isn't telling us the full story yet. It's just saying, okay, if we're to target at a particular time, then at that same time, this is just the influence or the signal variance at that time. It doesn't tell us anything about the future time. Now let's look at the future time. And so what happened here was if we observed it, or if the ETKF is predicting that if we target way upstream here, then the signal is likely to just diminish in magnitude, and it's just not going to reach the area for which we want to improve our forecast. Here, if we target the front, then the idea is that, well, we're reducing our error variance and our wind and temperature along the front, and then that front's just going to amble along towards Washington and Oregon, and it's likely to reduce our forecast errors just along that front. And so it suggests that the right-hand deployment is better than a left-hand deployment. Now we can do that with any number of deployments really quickly through all those factorizations that we were going through. And so we can come up, let's just look at the shading right here, with a summary map, which is essentially this amount of signal variance that's averaged within this area. And so this small value here, which is less than 50, it corresponds to up here where we're targeting. And so it didn't even get a shading when averaged. It was just suggested to be that poor of a location of target observations. This one, on the other hand, had an average value which is somewhere around 60 or so. And other areas, if we play this game over and over again, suggesting that we should target somewhere in the orange area. That's an optimal area to fly. And so what's done in practice is that a bunch of flight tracks are designed, and now they're designed off Japan as well. And then whichever flight track traverses the maxima of the summary map, or more directly, one can compute the signal variance in the verification region as a function of the flight track number. We can then hit very quickly our flight track that we think is optimal. So that's just how the ETKF predicts, in an operational sense, where we should target our observations. I'll finish up here just by identifying some of the challenges, and these were brought up by Pavel last week. One is that with all ensemble Kalman filters that we have spurious long-distance correlations. And so there have been localization methods that Pavel described on Friday. But we've got problems with our targeting. And if any of you could solve this, then you'd be famous, at least in my world. And it's just, okay, one can localize at initial time, but how do you propagate the localized covariance forward in time? That's something that we haven't solved yet. That it's just not clear how to do that theoretically in our world. Unless you assume something about, say, motion of the wave or motion of the disturbance, and one could possibly do it, but it's always going to invoke that assumption. A second, and this was already discussed a little, is that we're violating quite a lot of assumptions of linearity here, and the ETKF would only be perfect when linear theory holds in a perfect model. Then we've spoken a lot about error covariance matrices that are built on ensembles, and the problem here is that there's only one operational model right now, the Canadians, who use an ensemble Kalman filter in their data assimilation. So we talk about them all the time, but really 4D VAR is the dominant scheme right now. And because of that, we do have a real inconsistency between our error covariance that we predict and the error covariance that's actually in an operational data assimilation scheme that's assimilating these expensive observations. And the model error is very tricky issue as well that we haven't really addressed. So I'll stop there and appreciate your time and be glad to take any questions.
How much does it cost for sending such a plane?
Probably about $50,000 in total per flight, and that includes excuse me, the crewing, the overtime, the aircraft fuel, and then the drop zones. The drop zones are about $400 each. I'm not quite sure what conversion rate you want. We'll multiply it by 6.
Expensive, I wasn't expecting it to be much more than that. So that. And I'm a bit surprised that you're grouping so many songs, because I had the impression that you were saying that you wanted to be more or less to have a synoptic map. You were saying resolution perhaps of 1,000 kilometers or something like that. And you're, unless I'm wrong, but it seems that your dots are separated by less than 1,000 kilometers.
Yeah, so separate about 100.
So is it really worth doing such an oversampling of the data?
Yeah. The resolution of the operational data assimilation is about 50 kilometers or so. It depends on the model. And so the idea is to try and hit most grid points here, and at least in the NSET scheme, I haven't looked in others, that there's generally a fairly local influence from each of the observations. So what it's not doing is just able to correct the synoptic scale with 1 or 2 observations. So we need to pound it with observations to say correct a wave. So even though we're correcting something that may be a relatively large wave number, we still need, in reality, quite a few of these observations just to really pin down the characteristics of that wave. That 1 or 2 observations isn't going to do it.
I'm guessing that, of course, that's the whole principle of your method, but you are going to put more weight into that data than you will put on the routine data.
A little,
just the
yeah.
weighting of your data, saying, okay, this value is going to be 10 times more important than the other one, and I'm going to make it influence over a broader area?
Yeah, well, it depends on the model. That with NSET, that they trust the drop-zone data considerably more. But even drop-zone data have got problems. That drop-zones get blown around a lot, and it's very difficult to get accurate instantaneous wind speed out of the drop-zone as it's falling from the top of the atmosphere to the ocean. So there is certainly some serious errors, and also these are dropped mainly in weather systems themselves. So it's dropped in a jet stream, and so they blow around. And ECMWF would claim that their satellite data assimilation, they understand their errors and their correlated errors, and they've worked on that for decades. That these observations may not be that much more accurate than what they've managed to accomplish with satellite data. So that's a matter of debate.
About the satellite observations and the large number of observations we have, so that we actually have to thin down the number of observations.
Exactly. Yeah.
Could this adaptive sampling be used for how to thin the
Absolutely. Yeah, that's a very good question. It's something that I'm starting to work on a little. ECMWF has taken a lead on that too, like they have with many of these issues. Just to give a little background information on your question, that typically I think about 100 million radiance data points come in every 12 hours or so. And so even ECMWF can't assimilate that volume of radiances in one 4D VAR cycle. So they have to reduce that by 1 or 2 orders of magnitude. And so they adopt a technique that's called thinning, And what many operational centers do with thinning is that they essentially just average out the radiances or remove some of the radiance data just to thin out the number of observations. Now your question is, well, can a technique like this suggest where we should perhaps thin more, where we don't need the data very much, but then take extra data and have extra density data in our target areas? And ECMWF did a study on that. It just got published, I think, a couple of months ago, where they found that if we double the resolution of the radiances in the singular vector target areas, then it does considerably improve the forecast. So that was quite a striking result there. So I think that in the future, over the next decade, we may be moving more away from the aircraft and more towards intelligent satellite thinning algorithms. Great question.
How do the targets of observation compare to use singular vectors instead?
That's the rest of my talk. I can show you offline. So in terms of the target areas, let's just give you one example here. Let's just look at the top left-hand corner. So the red one, the red versus the black. So the red gives an ETKF target for a 2-day forecast. I believe it's 2 days. The black gives a singular vectors. And here's a case where they're actually very considerably out of phase. Now what we found when we did this comparison for winter weather cases was that the small scale aspects tended to differ quite a lot. Just so even on the synoptic scales. We did find a few similarities here and there. Here's one case where there was similarity. There are 2 maxima here, actually corresponding somewhat to a couple of weather systems, though they're not just hitting the vorticity maxima there. So there are some similarities and there are some differences between the different targets. The ETKF targets tend to be fairly broad, at least they did back then when we published this. In terms of which technique is better, it hasn't really been proven yet. But I think for the short range that both techniques have been shown to be quite effective. So short range means 1 to 3 day forecasts. Since we're able to use the ETKF out to 7 days, and I'll present that at the university next week, that I would claim, but obviously I'm a little biased, that the ETKF has a little bit more versatility in looking at longer range forecasts. So for mid-latitudes, I would say that, yeah, they've both got their respective advantages and disadvantages, but it's tough to say whether one technique is better. I mean, they're just different techniques. One could actually apply an ETKF on singular vectors, and I've got a few equations to show that we can discuss as well. That one could actually marry the 2 techniques as well.
Very general question, perhaps. It seems like the very problem you're having here of targeting observations in some particular sensitive area or important area for the evolution is sort of the same thing as when initializing an ensemble, right? You want to initialize and have the ensemble members differing in precisely those areas. So could you comment on the relation between these 2 different problems? Are they the same problem, or is that?
Yeah. Yeah, it may be easier to explain this in terms of singular vectors, because the way that centers such as ECMWF and the Japanese Meteorological Agency, they initialize their ensembles, is via finding these structures that would grow optimally from some area, which is to be determined, to then maximize the spread and at some future time, 48 hours from initialization. Now, singular vectors are also used in targeting with exactly that kind of principle as well, that the singular vector is supposed to identify where errors may be growing the most optimally, and so that is also a useful place to sort of pin down with observations how to curtail the growth of those errors. So there's a very distinct relationship there with singular vectors, or correspondence rather, in terms of how ensembles can be initialized and in terms of how observations can be targeted. Now, with an ensembles perspective, that the ETKF or other variants are also used to initialize ensembles, and Pavel presented a little bit of that last week. And so there are theoretical connections there also between ensemble initialization, where essentially there are areas where analysis errors may be significantly different, and that's just computed through the transformation of ensemble perturbations. That's also an area where you might want to observe and target. So yeah, both in the ensemble world and in the singular vector worlds, there's a distinct connection between targeting and initializing ensembles.
I think this, so I have a question too, but I think the key difference is that you also need to keep in mind that when you have a singular vector, it gives you an idea of the growth, but you need to worry about the initial uncertainty in that direction as well. So you may have something that you expect in a perfect model world would grow the most, but the uncertainty, if that's over land, the uncertainty there may be very low compared to something where the growth would be the fifth or sixth singular vector, but it's over the Pacific or the Atlantic, where the uncertainty is much higher.
No, a good singular vector scheme should be able to account for analysis uncertainty and scale its perturbations accordingly, knowing that there's relatively low uncertainty over land. And the same with the ensemble initialization too. It's a little bit more explicit in the ensemble initialization that the uncertainty is accounted for because it uses a routine observational network to squash down the analysis error variance over land. In the singular vectors, they should be conditioned on those sort of estimates of uncertainty, but they aren't right now. So, yeah, that's a good point.
So on one of your sort of next to last graph, you were showing the the colored region depending on the colored region of impact for sampling different places.
Yeah.
Yeah, I think maybe the next
Next
slide.
Computers are all slow here.
It doesn't want to go. The bottom one there. So
Sorry.
So if you just took a passive tracer at every point and measured its RMS distance from the center of your target, that's it, right? So just nothing sophisticated at all. But you just take each point, integrate it, follow it in time, measure its distance from the center of your target. How different would it look from the graph you have down here from the ETKF?
Yeah, I actually played with that a little, looking at just the particle trajectories from Japan and just tracing those and comparing them with the signal variance predictions. And well, that's essentially an advection speed there, whereas the mechanisms for the propagation of signal variance are hypothesized, but I'm not 100% convinced. We just published on it. It's hypothesized to be more associated with downstream baroclinic development, and so there's some sort of large downstream influence that appears sort of over 1,000 kilometers, 2,000, 3,000 kilometers, that isn't really caught just by a trajectory analysis. So it's a little bit more complicated, the nature of these targets and signal variance propagation, than just sort of following a...
I agree. It's a lot more complicated.
Yeah.
And if you could only fly on 1 out of 3 days, and you were trying to decide what the impact of the flight would be, then the value of doing the ETKF is clear. But if you're doing it operationally every day, then you're not using that information. And in that case, I'm just curious, how different is it from just? I agree, there's a lot more information. But how much, if you're going to pick a flight on one vessel, how often would it choose a different flight path? How often would it choose the same flight path? Because it's an easy calculation.
We've noticed that, in terms of climatology of flight paths, that there's number 46, and then there was one called 37. I don't know if I plotted it. It was around there. But they tend to be fairly similar. It's almost like one could just set up a routine, some sort of routine observation network there and be done with the targeting, I think. So yeah, these areas may not be quite so mobile from day to day, but it depends on essentially the position of the jet stream. Sometimes you get a subtropical jet splitting off, then it lights the southern region. If the jet stream really stays to the north, then the Alaska flights tend to be more important. But they're more sort of broad regime changes that these targets are
That you might see
associated
in a simple
with.
advection as well. So.
Yeah, I'll have to check that. I mean, we did look at the advection a little bit, but we couldn't really find much of a connection between that and the signal variance propagation. That was actually Dan Hodis's hypothesis. He said, well, look, you're talking about downstream development all the time, but isn't it just advection? I said, well, let's try it. And yeah, we couldn't really find much of a clear relationship between advection of a particle and the propagation of the influence of observations.
Well, just as a comment, we have actually a piece of information. Another way of doing observation targeting is through adjoint sensitivity. We look at a particular feature in the prediction of which one is particularly interested. Possibly on the basis of a forecast which says that something unusual or of particular interest is going to occur in this or that area. Then an adjoint sensitivity computation is performed for the feature of interest with respect to the initial conditions at the time when that observation will have been performed.
Yeah, the nice thing with adjoint sensitivity is it gives you a very direct dynamical meaning on saying if you perturb this baroclinic zone, then this is how it's going to influence a state estimate later on. With the ETKF, it's a little bit more difficult to interpret since it assumes the ensemble-based assimilation of observations. So the ensemble techniques have a lot more of the machinery of that long list of points that, because it's observation sensitivity that involves a data assimilation scheme. But the adjoint, I think, gives a much cleaner dynamical interpretation. And actually, much of the time, I think, where there's high analysis sensitivity, really, that's where we should assimilate observations anyway. There are actually about 10 different types of targeting techniques. So if you've got 10 hours, then I could go through all of them. There's adjoint sensitivity, and then there's singular vectors that use adjoints and compute optimally growing modes. There's actually adjoint sensitivity applied to tropical cyclones that actually looks at the adjoint sensitivity of the steering vector specifically to changes in initial vorticity. So yeah, adjoint sensitivity is a very powerful tool in many different types of applications.
At the same time, I think it is fair to say that, at least so far, observation targeting in the situation where it has actually been implemented has not been considered as very successful, and at least not successful enough so that meteorological services and anyone is actually trying to implement that in a more or less operational way.
I think that's more a European view, and that's probably fair enough. There are just generally higher predictability cases in Europe. With this stuff, the program's been going for a decade, and they keep doing it, but they're not really evaluating it. So it may be the same issue also for the US, at least for the mid-latitude targeting. The problem is they're not being evaluated that much, but then the US does have some advantage, advantage is not the right word, but the US may, there are reasons why it's thought that the US targeting may be more important in terms of improving forecasts than for Europe, and that is that the analysis errors in the mid-latitude storm track in the Pacific on average are huge. They're much bigger than in the Atlantic, particularly this kind of region here. So there was a paper, Rolf Langland and some others showed that. And then also, I mean, this is a bit of a silly reason, but the GFS doesn't use satellite data as well as the ECMWF. And so the US models are finding that the droxons still produce some impact. ECMWF has advanced so far ahead with satellite data that probably these droxons are redundant. It's just a small number. I'm also going to say that for Asia and for tropical cyclones, that the targeting is really, really useful. That it costs $1 million to evacuate a mile of coastline, and so any improvement that we're getting some considerable improvements in the forecast just through flying around the storm and hitting a couple of target areas. It's set to stay really for tropical cyclones for a while, but the metric is so much easier to define for tropical cyclones. For this, I mean, what do we define here? I mean, do we define winds and temperature, or it's just even the evaluation metric is not very clear in the mid-latitudes. So I would mostly agree with your assertion, but I'd say that, yeah, the opinion in Europe is a little different to that in North America.
So this thing on the metric, I mean, I agree there's not a unique metric. But if you systematically don't get improvement in most things,
yeah,
if the metric actually matters, if you need to take temperature and not wind,
yeah,
then that's telling you a lot.
Yes, it is. Yeah.
And also, it's just this comment on what counts as targeting and what counts as additional observation.
Yeah.
So there's a nasty analysis error off the west coast, and the Pacific is bigger than the Atlantic. So plugging that by always running 46 versus trying to shift between them. That's the interesting question.
Yeah, and that distinction is fairly blurred in my mind. That I'd rather sort of move away from just calling everything targeting and saying, well, we need to just improve our routine observational network just based on the flow regime.
So outside meteorology,
we don't need
targeting.
The
distinction is really clear.
Yeah,
and it makes it harder for people outside meteorology to actually understand when that distinction isn't tested.
Yeah, it's a little too blurred for us. But yeah, especially with satellite applications, I think that we don't necessarily need ETKF or any targeting technique. Well, maybe we do for thinning. I think the question about thinning was really important, and I think at least it was shown for signal vectors that those were targeted and those were making an influence. But they only compared it against random. They didn't compare against some intelligent use of the routine network, such as, like, say, a 46 if there was a subtropical jet. It's not a very strong distinction.
Another question. In typical operational environment, you have every few hours you make a new analysis. And can this method account for this impact of these observations after you make a new analysis of new data?
Yeah, that's something that with ETKF we're very sorely lacking in. And well, all techniques actually. I mean, we're probably closest to doing anything on it, but all techniques really lack that. So if we go back to this, that here's our observation time here. None of us account for all these times, which could be like 2 days or even more. We don't account for routine observations that are assimilated at all of these times. So that's quite a big failing, I think, on the part of all of our techniques. Whether it makes a difference in terms of target areas, I think none of us are really that convinced that it will make a very big difference. None of us have been terribly motivated to do this. I found that the shape of the target areas is fairly robust to sort of big changes in the error covariance matrix. What we do and what I didn't show was that with ETKF is now we just transform a routine matrix based on estimates for analysis error variance, and then just say, well, because of that, we're implicitly assuming for these, but not explicitly. But it's a little bit of a workaround, but your point is well taken that we don't account for that.
You already assume the dependence between the routine observations and so it's only based on your assumptions.
And we still need some decent estimate of what analysis error covariance would be at this time based on routine observations.
And those routine observations may include an adaptive observation in the middle of this period.
Well, it may include previously taken adaptive observations.
Or even one that you know, even the one you requested yesterday.
Yeah, exactly. Yeah, I mean, those would be the most important ones because there's still some memory of those observations a day later. Yeah, that's an important point. We did play a few little games with that.
And how much trouble do you have with air traffic control? Because in the Atlantic, this was a major problem.
For this, well, it's gone for a decade, and really, I think the system's just really down. That there's no issue at all with air traffic control. I mean, for our field experiments around hurricanes, there are problems because of Cuba and Venezuela, and there's all kinds of issues. For the Asian experiment in 2008, there are issues with air traffic control. There's some issues between Philippines and Japan. So, yeah, it's really for this part of the Pacific that I guess no one really cares about. It's between Hawaii and Alaska that is completely fine. And it seems like flying out of Japan as well now, which G4 aircraft has been doing the last couple of years, there's no real issues with that for winter targeting. Way over.
Well, I think perhaps if there are no more major questions, we could go on to a discussion about the way to go on with the program. And so, I guess it's Axel and me, or
Then we should think. Maybe.
yeah. It was interesting in the audience. So we have a schedule now only for talks tomorrow by Jenny Smith here and Wednesday by Farhan here. And for the rest of the program is not yet decided, and that is something that we should discuss now. And the main idea is here to have perhaps one talk per day seminar like this, and then perhaps also some of the days some targeted discussions with some maybe short presentations from maybe more than 2 or 3 people on some subjects, and then a general discussion. So
Yes. There's at least one constraint for this week, which is that we have a licentiate defense by one of my students in solar physics, and that is on Friday afternoon between 1 and 3 o'clock. It is an open event. You are welcome to come there, and one of our participants is actually the prime opponent for this defense. That's Mazumi Dikpati. She's also in solar physics and has been involved in solar cycle prediction. So that is one constraint that we have for this week, and it might also imply some additional things. I mean, one of the things that Jonas has been mentioning to me over coffee this morning was that since we have a diverse group of interests from meteorology to climate, and then now even astrophysics, solar physics, and also turbulence, it might be a good idea to have a more introductory talk towards the main differences that we are exposed to when we are dealing with solar physics issues.
I guess the issue is here, I mean, this is a mature field. Data simulation prediction is a mature field. It's been going on for decades in meteorology. It's very new in solar physics. So it might be a good idea, I mean, to try to connect people here with these two fields. Perhaps that someone could give an overview of the physics and what is the state of the relation in general about what is the main characteristics of the flows and convection, whatever it is. So before getting into, so that you have some feeling of physics, how simulations are done, before even discussing data simulation in that context, so that metrologists can sort of connect to the dynamics of that.
Yeah,
So that is.
I have no idea about how a solar dynamo works and what the models are that
I think that's
exist.
understand that there is one difficulty that we have magnetic field.
Yep.
The key problem is linked to the magnetic field, and we don't have the equivalent to what you call the primary equation. We don't have the MHD equivalent to the primary equation. Mazumi Dikpati did develop in HAO with Peter Gilman and Mark Misch the MHD shallow water model to try to take into account aspect of the magnetic field. And I think that's perhaps what is the closest to what we would call primary MHD equation. Right now, the big problem we have with the solar physics aspect is that we have sunspot emerging, and we have difficulty even Axel and I perhaps don't totally agree on where the sunspots are formed and where we come from, you see. So right now, even in the from the theoretician point of view, we are not yet totally in agreement on where the sunspot comes from. And the big difference is that the activity itself of the sun is driven by the continuous emergence of flux from the dynamo process itself, like you will have on the Earth core. But also we have this emergence of flux on intermediate scale, so it's not the global field, it's not the small scale stuff due to the dynamo at the turbulent scale level. It's this active region that pop up at the surface that is very difficult to I don't know how to include. We tried by this simple model, also me and stuff, and that's where we have an issue.
I think a possible way of saying it is that for the solar physics case, data simulation, we want to use it to figure out how the sun works. Okay. Instead of where meteorology know how the meteorology works and apply it in a forecast mode. Of course, we also want to do the forecast, but in a way, use data assimilation as a way of inferring what physics to use to model the system.
So perhaps if someone could then give a talk where you explain, I mean, surely some parts of the solar dynamics is known, but there are the unknown questions that you want to answer with the help of data.
I think it would perhaps be useful that we give two short talks that would be different. I can certainly give the talk on convection and magnetism. I think it would be worth that Mussolini give the one on perhaps the mean field solar dynamo model and what she has been trying to do, you know, and because
to know, what is the question you're
I think there is a difference. I will say that right now, and Lauren also and Olivier, we have been working on an adjoint model. I think there is a difference right now. We are more in the solar physics context. I will say we are closer to what climatologists want to do. So we want to predict mean temperature variation. By that I mean, when is the next solar maxima? How important it's going to be. We are more in a situation where we are trying to predict global structure in an average sense, where meteorology is already so advanced that it's trying to predict where rain is going to drop. We are not at that level yet. We are more in the level of saying more in the seasonal prediction aspect, if you want, of the physics.
Trying to predict ice ages from
yeah, I'm not really sure what the situation in climatology is. Certainly, Olivier, you know more where it's.
The point is that seasonal prediction, except predicting, of course, the seasonal cycle, is actually more difficult predicting when from Chile from South. But yes, predicting the average weather for next summer, kind of average, I mean, a deviation from climatology for next summer. Whether next summer will be in some areas warmer or cooler than an average summer is more difficult than predicting weather in 3 days from now, I think, for instance, Stockholm.
Yes, but you don't have with the climatology, you have less this problem of the Lorentz window of saying you cannot predict weather more than 10 days or 15 days from now.
Yes.
But what's the window for climatology or for seasonal prediction?
Well, we don't actually already know. We don't know enough about the very process which govern the fluctuations of the weather, but we govern what we call the interannual variability, the fact that the weather isn't the same every year, even you have an average of about 3 months. We don't have enough understanding of those processes to be able to understand the question.
Yes.
So for me it sounds a bit like that the problem on the sun is a bit similar to the problem we have in the Earth system with the El Niño Southern Oscillation, where we have a hierarchy of models from statistical models to simple models with a few parameters up to high resolution, three-dimensional coupled atmosphere ocean models. that try to predict the same feature, but on very different levels.
I should probably emphasize that solar physics does not necessarily mean that it has only to do with long-term issues. There's also short-term issues for the sun. I mean, we have what is known as space weather, which are short-term phenomena. They happen on the time scale of even microseconds, but more importantly on the scale of hours, of course. And they affect particle storms in space, and that's relevant for astronauts outside the Earth's magnetosphere, but it's also relevant for many satellites. And so these are short-term phenomena, and they depend on the particular, I mean, ultimately they depend on the nature of the convection just below the surface. And
the structure of the active region.
yes, or the structure of the active region. And so that really connects with the local structure of the turbulence that we have in the sun.
Yeah,
So
but then we are in
these are shorter time scales,
we
so
are
that's more like the weather.
We are in a situation, even if it's a terrible what just happened in US, but we are in a situation of the people who are trying to predict tornado in Alabama, and they completely screwed up, and there are 300 people who died. You know, so we are a bit in this situation where you know that there is rotation, vorticity involved, or magnetic helicity in the case of the sun, where you have is that system going to blow up or not? Is it going to create a tornado or not? And this is subtle.
Right. That's right.
So I think I agree almost more with what I thought you said at first, which is a comparison with real climate as opposed to decadal or 20 or 30 years as opposed to seasonal. I agree with Olivier on the seasonal stuff. There's a nice paper by Ed Lorenz in the early 70s on seasonal forecasting, just pointing out why it's different, but why we also don't understand enough. But I'm also not clear how much do you, depending on how good the models are, I'm not clear what you want to call data assimilation. I mean, there's an issue of model evaluation, which is which you want to do even when the models are not very much like the observations. But to try and do data assimilation in a case where you're trying to select between model classes, I'm not sure data assimilation can really tell you that unless the models are all very, very good.
That's what Andreas suggested. Yeah, that is probably a doubtful issue.
So that's the question. Is okay? Can you leave data assimilation in order to do that sort of model evaluation? What are you more interested in?
Yeah, I think now is not the time to discuss these issues, really. We want to find out how to organize the program here. And I think from the people, the fine people will be here, we should have some session about these issues this week. Is that correct? Probably then Thursday would be a day.
Is that to be good for you?
It's not a bit too late. It's not already too
late. Yeah.
Tomorrow will be more. I mean, we want to be able to interact. You know?
Okay.
Well,
we have a seminar scheduled tomorrow, but we are just a little bit afraid that we cram the schedule with too much scheduled activities at the same time. So it depends on then. Would it be too much if we have? I mean, your talk is before lunch in the morning. In the morning.
And what about this afternoon? What's planned?
Today is the afternoon.
Yes.
Nothing. Planned.
Because I have already a small presentation that I have already gave.
Sort of a primer on solar physics.
Yeah, well, kind of what's the situation in solar physics, and I'm sure Mosumi has already a short presentation where she can show what she did, you know, and we have, I guess we have already, we can go fast enough that I think the earlier is the best.
Yeah, agree. Absolutely. And then, so if everyone, if no one is against, we could have some introductory presentation of the issues here already today after lunch. So,
I agree.
Yeah.
So, what would be a good time, for example, 2:30 or 3 p.m.? To leave time for people to do something after lunch? Well, when do you usually start the day? At 6?
Yes. Actually, there's another slight constraint, and I call it actually a stupid constraint. That is,
it's a constraint.
which is a constraint which I have been trying to oppose for the last 3 years. There is what is called no-reader coffee, which is Mondays at 3 o'clock. And the one thing I'm strongly opposed to is simply the fact that this coffee always excludes the program participants. And I think this is really just an outrage.
And what would
and you all agree,
obviously.
You hopefully all agree with me. And the most stupid thing is that actually one of our students is today in charge of organizing the cake for that, which is Jörn, who is actually also the one who is doing the essential thing. So I would think we should somehow use it as a constructive protest, perhaps. So maybe what we should do is organize also a coffee. And then
this is internal matters. So what I have my own institute.
What is the program? Lolita has the coffee, and we're not invited. So what is the program? We said that you must be present.
No. I mean, if I don't want to be present, then I'm not there. I mean, nobody else.
So we don't care. Well, we don't really care.
What is your problem? No, we can have. No, we can have presentations including during the Nolita Cafe, and if we want a cafe, we have to do our cafe, we may have it later.
So what if we have the coffee here and we invite the Nolita people to take coffee with us?
Yeah, that is possible. And the question is also, when do we want to talk? So what we could do is we could simply say we have coffee at 3 here also, in the room, and then we can in some sense merge with the others, but they are all sitting in the coffee room.
Would it be possible to have these introductory talks before that, and then coffee and then discussions? Is that sensible?
And I mean, but we wanted to do, yes, we wanted to have the discussion or talks about the solar stuff immediately after that, right? That's fine. That's what
well, or before coffee, that's also possible.
Yeah, but that gives less time. What do you think is better? To do it at 3:30 immediately, at 1:30 immediately, or after lunch?
What did you do usually? I don't mind I think we don't mind speaking at 2, having a break for the coffee and restarting after. I don't know, or we do it after at 3:30 until 5.
Do we have to have the coffee at 3, really? Or it could
No,
be
I mean,
from 2 to 4, we have the talks, then we have the coffee, then we have discussions until 6.
At 3. But how long are the talks?
No, I want them to be short, I think, because we want the point to be across. It's not a question of doing a lecture. I want it to be concise. So we say what we need, 25 minutes plus some time for discussion.
I think that's really part of the question, is this issue of what you want to try and get out of it. I mean, we never saw the Navier-Stokes equations this morning. So this is what you need to have. You need a broad brush of how complicated the model is. But the techniques we saw this morning don't really require understanding the details of how you do the flow. The question is how complicated is the flow, or if you have a statistical model. It's very, like you say, it's a very concise picture. How good is it? What does the output look like compared to the observations?
I mean, we are not there.
Yes, but
what we are doing right now in solar physics are basically 2 models. Either we are in the meridional plane, not the kind of things that Mussolini is doing and others, or you are in the surface. So you don't have any information with depth. And these are the kind of models that Schreiber and De Rosa are doing, or Wang and Chili. So we are just assimilating data at the surface and propagating them. Then there is some people who are doing what we call, going back to what Axel said about the emergence of structure. Some people are taking what they call magnetograms, that are the observation of magnetic field of sunspot. They use that as the initial condition to reconstruct the field, and then they let their model evolve. They are not yet in a situation to do data assimilation of these models with observational as the models go along.
So understanding those connections are sort of what would help us understand better what are the relevant techniques.
My talk is about that, and I think it's a 20 minutes, 25 minutes talk maximum. So I think in an hour time between myself and Musomi, we have more or less wrap up the main current situation.
So could it be reasonable to start at 2 o'clock? And then finish those at 3.
would you be available also after lunch?
I had not actually planned to be here after lunch.
Yeah, but maybe you could. I mean, you're not after lunch at all, yeah?
Sorry?
You're not after lunch at all, yeah?
Yeah.
Ah, then it doesn't matter anyway. But I would, I mean, I can imagine that it would be really a pity if we feel that we have to cut it short after 60 minutes. And
No, it just means that there is a coffee break, and then can resume, and even maybe during coffee. That's,
I don't really mind. As you are here, you know better. If it's better to start after, then it gives us some time to prepare the things, and we say, okay, let's do it at 3:30.
Yeah, I think
And from
I
3:30 to
personally
5.
think this is optimal to do it at 3:30.
Yeah, actually I will also need some time to prepare
Yeah.
because I didn't...
Yeah, let's do that. Like this, when we come back from lunch, we can gather and put some things together, and perhaps we can show a little bit of the assimilation.
Yeah,
We can
why not?
merge things and have a two-talk, person talk for Lauren and I, and Mossoni. Yeah, let's do that at 3:30.
okay. So that's
Up to 5, let's say.
okay. So that means you have some presentations, and then discussion after that. Maybe. Okay. And who?
Do you intend to?
Sorry?
No, it was a question to session. You want to present only the critics of your program, the context in which you want to try to have assimilation or
Yeah. And also, you can put Lauren.
Yeah, that's right.
And Lauren. Lauren.
And you will be here after. After you will be here.
Yes.
So you can share.
I could at least find some other German pads, yes.
So that's the program for today. I would like, we have, then we have Thursday and Friday, which is what was not decided yet. Tomorrow you will have presentation, right?
Yeah, so there's one issue that Leonard and I discussed yesterday, issues connected with turbulence. And so I asked already Yukio Kaneda, because he had written a paper in 2005 about the impossibility of data assimilation in turbulence, which might be an interesting subject for many of us. And it's actually also connected with your talk perhaps in the morning. And I was thinking you might also be interested in being exposed to that discussion. So that would be an aspect that we could have either on Tuesday.
Tomorrow.
That will be tomorrow because
Discussion in
leaving
connection to after your talk.
Wednesday morning. Would it be good to do it directly after your talk, do you think? Or would it be better to
Probably better in the afternoon.
in the afternoon, yeah? And would anybody else be interested in saying a few things? So, I mean, something which is controversial and something which is which is opposing his claims. Maybe you agree.
Did you say we're oceanographers here? How many ocean people do you have?
I don't know how many.
Any other oceans? So I think the ocean is another place where there's a lot less legacy code and data assimilation. Where I think the sort of discussion could be the sort of discussion of new and different ideas which work better. Might be it.
Yes, well, I will show you how we do data simulation. Working in data simulation in operational center for the emergency, so we have an operational system doing data simulation for 10 days forecast. So maybe I could give an overview of what we are doing and what are the main issues we have.
Yes. But
First, is that already tomorrow? That's
I don't know.
I mean, that might be, that's certainly interesting. The question is that also connected to the claim of data assimilation being impossible for turbulent flows? That's what you would be saying.
It's more under-observed system.
It's an under-observed system.
Does anyone think it's possible to assimilate?
I mean, that was probably my naive perception of what Olivier said. That it's possible to some extent. When you are saying data assimilation for turbulence is impossible, would you, and you don't know any background of that, would you first of all say yes or no?
Well, turbulence. Large-scale atmospheric circulation, turbulence and assimilation is possible for it.
Yes.
So I don't know. It's all a question of, no, it's largely a question of time scales of, two time scales. Time scale over which you observe system evolves, and time scale over which you observe it to some degree of accuracy. If, of course, the observations are very sparse in time with respect to characteristics and time scales of different processes, you cannot do assimilation. If your observations are dense enough time, then you can do assimilation for both processes, which you are doing some type of residual assembly in matters.
So if we focus the discussion on timescales of predictability, that would capture both yours, but I'm not sure whether that would capture yours.
So I think a number of the things that I say will be in the morning. So maybe the afternoon on time scales makes sense. But I think that also be interesting to you too.
Sure. So, if I remember correctly, your talk was on something. And then in the afternoon, some introduction by Tanya, maybe. And then discussion on time scales.
Would that be something? Or would Olivier need to do an introduction on that? On the timescale issue?
I can do introduction, but usually it will be rather, I would say. Okay, I can do an introduction, but it rather, to a large extent, it will be simple and I would say, rather.
Simple is good.
Yes. Right, so that sounds a possibility. So Olivier would give a short introduction about what we can at most expect in terms of timescales. And then Mr. Caneda can report on his earlier work, 2005.
And that's tomorrow afternoon.
Yes. What time was a good time? I mean, actually, 3:30 is maybe a good time. It's 3:30. What do you think? 15:30. Yeah. We are too rushed after lunch. What?
I cannot go for the
I see.
Okay. Yes.
On the theme of different timescales, I maybe could contribute with extended range predictability in the atmosphere-ocean system. For example, seasonal forecasts and even longer decadal forecasts.
Is that connected to ocean data assimilation?
Yes.
Or timescales. I was thinking you were talking about timescales here also, or are you really open to
In my case, in our case, we don't do this. Actually, I have a colleague who works on that, but I can't say very much about it.
We couldn't fit too many things into these, too many presentations tomorrow after another work. So we could have this perhaps a later day in the week. Of course it's connected, but it doesn't mean we have to make all statements at the same time. What do you think?
Depends whether it's related. What do you feel? Do you feel
it's related, but it could fit on Wednesday afternoon as well, I think.
Wednesday.
I think it's more directed at practical prediction, you know, using real models and things that perhaps these principal issues.
So I'll say something. I may say something about seasonal 5-year sort of forecasting in the morning. So sort of the time scales at which you could expect to get something out of a model. And it just, yeah, I mean, I think that it really is relevant. So,
okay. By the way, when are you leaving?
Unfortunately, I'm leaving on Wednesday, so I won't be here with you. But
you won't be here on Wednesday afternoon, but will you be here before lunch?
No, I'm only here tomorrow. Okay. But, yeah.
If Linus can focus his stuff, then it might be suitable, right? Yes.
Yes.
Perhaps. It's very unfortunate I can't be here.
Wednesday, we have talks on it. Yes, that's at 3:30. That is actually 1:30. This is 1:06. Okay.
Yeah, I'm flexible with that as well.
If you wanted to have it at 3:30 instead?
Anything, yeah.
Would it be, yes. Yes, 1:30 is an established time when the we normally have the journal meetings, and we don't have a meeting then anyway, so that was one of the reasons why I thought of 1:30. I would be here, however. And on Thursday, there's a journal Arbor Nova Nordita colloquium, which is outside our program, but I should tell you about that. And the speaker is Yuzong Haim, and he's a distinguished professor at Seoul National University of Korea. He will talk about clean and safe energy storage materials. So that is a link that you find on the agenda system. So some of us might be interested in that. Normally a colloquium is of course something that everybody should be interested in. And so therefore I will normally go to that, and I think we should not schedule anything exactly at the same time. That's at 3 o'clock. 3 o'clock. Or rather 3:15 with coffee starting at 3 o'clock.
So the best is if we have a before on Thursday, that's best before lunch.
Yes.
Yes. 10:30.
Yes.
There's nothing decided yet. Should we decide that now, or should we? One thing I also would like to do is to encourage you to talk to each other and try to come up with other. I mean, we now have one sort of discussion, or I should say 2 areas of discussion here, but some common themes that several of you are interested in, and where you would like to sort of organize a discussion session with maybe a couple of two or three short presentations, and then some discussions, so that you can yourself find out other ideas for this. The question is, should we decide now on a talk before lunch on Thursday? Something for Friday.
Do we necessarily need to have something every day?
No.
Because then also, I mean, we are here to collaborate, and if we are always sitting here and listening, I mean, I'm fine with that, but the idea is perhaps to trigger some interest to people, and then they can perhaps sit down and discuss, and if we, as we go along, we have an idea for our talk, and further on we will do it. But my impression is that we need to have time to actually sit down and work.
So we can at least wait with deciding something for Thursday.
Yeah.
I agree, yes. You are here for the whole 4 weeks, of course.
Yeah, 3 weeks.
Yeah. You're not here for the last week?
Yes, because I have a meeting that has to come. So I plan to be here for the full time, but then
yes. Right, yeah. Yeah, thank you for reminding me. Okay, good. That looks like. Otherwise, please email us, of course, if you have any extra suggestions. I will use the agenda page to put in what we just discussed, and then I will send you a reminder about that also via email.
And to find this schedule, you click on the button contribution.
That's right, yes, that's right. And by the way, that's something which, where in principle other people can also enter something if they register as a user. So first of all, there's a login button, and then of course you click and then you say that you don't have a password, and then actually that one item says, if you don't have a password, click here. And so don't ask me if you don't have a password, but answer this question. And then you follow this thing, of course, and it sends you an email and stuff like this. So then you become a registered user. That means you can begin to schedule actually anything. Of course, we will see who schedules something, and if you're just doing wild things which don't have a basis, then somebody will ask you, what did you do? But in practice, it might be helpful because why should it all hang on my side to do these things? So often, I mean, Linux can, for example, register things. I can do, and a few others here can do that. But we can all give you access to also modify existing pages. Okay.
Okay, so we should have lunch, I think, and we'll reconvene at 3:30. That's time. It's really good.
Okay, thank you.